Hi, today I'm going to discuss about one of our products, RacEr, is a GPU. Before that, I would like to give a little bit introduction about our company, our technology, and problems in the industry, and more about products products now. Later, then I'll show you live demo about our GPU. So we are a startup company and a fabless semiconductor company like other companies. Our company is specially oriented towards solving circuit designs in a computer arithmetic, for example, in a floating point core processors or floating point arithmetic units. So these units are frequently used in artificial intelligence, machine learning, or high performance computing, you name it. There are a lot of applications which requires heavy math computing. So these math computing requires they are power greedy, and then they demand higher performance. So there are a lot of research, and there are a lot of innovation has to be done. So we are very excited with uh, this field, and we try to contribute as much innovative products as much as possible. So our most of our products based on a new number system called POSIT. POSITs are alternative to floating point number system. They provide much better accuracy, larger dynamic range than the FPGA arithmetic part. And apart from that, we have new technology called carry-free adder. Carry-free adder, this is a novel technology. We would say that whenever you do the math computation, for example, matrix addition, multiplication, or exponential, or any HPC domain or AI related, everything has to be computed in terms of addition or multiplication. So whenever we do addition or multiplication, so there is the bit has to propagate from least significant to the most significant bit. So this is a very time consuming and power greedy as well. So most of the adders nowadays in the state of the art processors have a carry propagate adder or carry link adder or other adders, but still there is a propagation of the carry during the computations. So when we do the carry propagation during computation, so that will suck a lot of power to compute next arithmetic bits. So what we have is that this CFA do not propagate the carry. All of the computation done in a parallel. So regardless of number of bits, the arithmetic computation in parallel. By doing so, what happens is that most of the dependent instructions, for example, if there is a complicated mathematical equations, those equations are computed very fast, and there is a least dependency between each instructions. So that is the power behind the CFA. CFA not only reduces dependency, it reduces the power, and it delivers higher performance in terms in a mobile or laptop. You may assume that in future you can watch videos maybe many hours without reducing the battery, uh, and we believe that uh, all the arithmetic circuit design has to be higher performance rather than building in a higher technology nodes. So the current problem in the industry is that most of, as I mentioned in the very beginning, is that all AI, HPC, machine learning, or graphic computing applications demand high math computing in terms of, let's say, in terms of matrix multiplication or TSP computation or a BLAS library and so forth. So most of these um, applications use floating point computations. So by using floating point computation, the data width is large. As I mentioned, the circuit becomes large as well as the power and performance power becomes high as well, and performance degrades. And if somebody wants to higher precision, they have to jump to the, for example, from 32 to 64 bit to require higher precision. For the higher precision, then there is a penalty has to be paid uh, in terms of performance. So the posits are very interesting number system. So they have a tapered uh, accuracy. I would say, you could say, in the left and right side of the on the slides here. So and they provide a few extra bits of accuracy. So these extra bits leads to higher dynamic range in terms of computations. As you can see, there are I have given certain closures here: addition closure, multiplication, and reciprocal closure. You can plot any closure you want. As an example, I have given only 3 here. So posits have I would say most you can say most exact results. There are no nans, and approximately 18% you could say the exact, and in any of the closure plots. So based on this number system, as I mentioned that in the very beginning, that we have a supersonic core. This is suitable for HPC. We have 64 cores inside in this core. Each acts as a CPU. And so it can do all higher end mathematical computation, for example, hyperbolic or exponential, trigonometric, or any higher mathematical functions you may think of. And we proudly say that we are the first to have a world's first POSIT GPU. So it can configure up to 512 cores, and it can deliver more POSIT per operations, more POSIT per more operation per watt. And it can support all floating point instructions, and it is similar to the CUDA programming model. Yeah, so I would say you don't need to change not much on the programming side. And the Falcon is suitable for AI. So here we in the Falcon core, we have 16 cores. It can support all matrix multiplication, additions, and the parameterization of processing elements. Um, it is So it is very light arithmetic unit. It has very light arithmetic units, which is suitable for in this A and ML. And TEDS is suitable for automotive applications. So in this product, we have 32 cores, and it is best suitable for automotive applications such as injection, ignition, timing, or brake assistance, or vehicle dynamics, so forth. So there are a lot of timing critical applications where most of the computation has to be done in real time and on time. So TED is best suitable for automotive. So we developed the product in a cloud. We used AWS as our development platform. We had 2 business model. One is we have our core in soft IP core. So we have soft IP core written in Verilog HDL. Those who wants to use our IP core in their designs, or they want to integrate in their designs, we have that Verilog code Verilog written codes. And the second one is those who wants to test, or those who wants to directly use our codes for their application development, or any benchmarking, or anything they want to develop um, applications. We have deployed our IP core in AWS. So on this slide, I'm going to show you, I'm going to discuss about how what are the steps involved in application of product development. So before using our product in AWS, you may need to go to AWS console and then register yourself. And then once you registered it, and then once you log in into your account, there is a AWS marketplace. In the AWS marketplace, you have to type or select FPGA developer AMI, then you get it from the Xilinx. From the Xilinx, you could say you could use instance. Choose the instance F12X large. So this one is Xilinx Alvia card connected in a cloud. I think is a north in US Northeast one region. Once you configure this instance, for example, memory, or how do you connect to the SSH, or and how much storage you require and so forth, then once you have that, you launch the instance, and then you connect instance to SSH in Linux, or in PuTTY if you are a Windows user. So that is the usual setup. So to demonstrate, we have developed a sample example for vector addition, vector multiplication, vector division, square root, and exponential functions. These are frequently used in HPC applications. So what we did was that these applications are deployed in a host CPU, which is x86, and the similar thing we deployed in RacEr, which is our GPU, and then the RacEr is shipped with we have our home built Vivid compiler. So Vivid compiler is a native POSIT compiler, which it supports all the POSIT 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 operations. So we have C and C++, and we do have a Fortran as well. In this example, I have not shown here. So the applications are computed independently and then compared in terms of the accuracy and correctness of the result. So this is the usual setup. Now I'm going to take you the live demo. So once you connect the instance, then you have to load this instance, the AFI we provide. Assuming that you loaded the AFI, then you just have to type make regression, then enter. So it will run through all the regression tests, and then it will tell you the results are most of the times matching. So note that since it's a different number system, some of the result may match or may not match. It doesn't mean that the results are incorrect, because so it depends, since the POSIT number has a huge dynamic range, so you have more accurate results than the floating point number system. And the customers we need to modify any programming model. Vivid compiler supports it is compatible with standard C or C++ programming model, and they don't need to initialize any of the cores. All of the taken care by our kernels.